Here's where we left off with the last acid-base lecture. This just talking about the pH scale being logarithmic, multiples of 10, inverted, so lower pH is higher acidity than uh, has a higher acid concentration than high pH. Negative, it does go into negative values, but I don't usually see that too often, but technically, theoretically, it could go from negative infinity to positive infinity. Of course, you can look up some of the acids. Might be a project you can do next week, looking at different acids and what they do, what they're used for, and their strengths that they possibly can have, but it can be negative. Usually negative 1.1 to about 15. Okay. One thing to note is that pH doesn't have, for significant digits, there's no unit on pH, as I mentioned earlier, but significant digits is kind of interesting because it's logarithmic. The significant digits, when you have a pH, are only based off of the numbers after the decimal. So if you have something of pH of, say, negative 1.1 here, this would have one significant digit. Okay. Because of the number after the number before the decimal, right? Because it's a logarithmic scale, those really mean the exponent, right? So this 15 here would be 1 times 10 to the negative 15th would be the concentration, right? So this will only have one significant digit as well. So the places after the decimal are actually the significant, how accurately something is measured to, right? Kind of interesting. Not that important, I guess. Let's talk about some acid strength here. We talked about strong acids and what those are. They completely dissociate, right? Here's the list of strong acids. When we talk about the acid constant, dissociation constant, for strong acids, we usually don't give one. It's hard to calculate. It's nearly or 100%. It might be 100%. And so the concentration is that constant is the concentration of the acid. So if you have 1.0 molar hydrochloric acid, right, that concentration is 1. And so the pH of 1 molar hydrochloric acid would be that's the concentration. That would be the minus log of this, right? So that would be 1 times 10 to the negative first. Okay, that would be the constant. I mean, the pH would be 1. No. This would be the concentration of the hydrochloric acid. So it would be concentration. So it would be the minus log of 1. So that would be 1 log of 1 is 0. So the pH of 1 molar hydrochloric acid would be 0. Right? Here's some acids that don't ionize completely, don't dissociate fully. These are weak acids: formic, acetic, citric, basically every other acid there is that aren't on that list, right? And so we talk about those. They can get from 1 to 5% ionization, okay? And that means 5 out of 100 atoms will ionize, right? 95 molecules don't. And so you have these really small acid concentration constants. But they both can exhibit pH readings. Just has to do with the ionization constant for the weak acid or the concentration of the strong acid. Okay. A little more about strong acids, just to reiterate this. They shift to the right. They completely dissociate. Usually this reactant does not exist. Here I've drawn it as a yield sign with a really, really small arrow there. It's hydrochloric acid. It wouldn't even be in that direction at all. So it's 100% or almost very, very close to 100%, 99.999% in the form of the products and no concentration of the reactants. Okay, so you have the strong acid conjugate pair. So for strong acids, equilibrium lies very far to the right, dissociates 100%, makes a weak conjugate base if you're looking at it the opposite direction, and can't really calculate the Kas. The concentration is the pH. For weak acids, right now we have the reaction shifting to the left. It means we have more reactants than you have products. So there's more of the acid undissociated than there is of the ions. Okay, so you can see those weak conjugate pairs. It means the bond between the ions is stronger to each other than it is to the water molecules. Just something to think about there. Mostly undissociated molecules are left over. Here's a little chart. It gives you the properties of strong weak acids. I'm going to pause this video and copy that down. Some details there. You have things called oxyacids. Talking about acids, this has ones that have oxygens in them, so they have that polyatomic ion with oxygens. Learned about those, similar naming. So maybe someone can remind me if we've done acid naming in this class before. Can't remember. And you can also have organic acids that have these carbon in them with these backbones, right? So you have this what's called a carboxyl group. So you can think about how that would bond together, has the hydrogen with these carbon and oxygens usually. They always make weak acids, acetic acid, formic acid, citric acid, things like that have these those are called organic acids. Just some more details for you here. So here's an example of a problem when you have a strong acid. Says calculate the pH and the OH minus. So it's asking you for two things here. For a 5 times 10 to the negative third molar hypochloric acid solution. Perchloric. What's the name of that? I forget. It's perchloric acid. Copy this down as well. This is this box is a good way to calculate strong acids or strong bases, for that matter. I didn't really talk about this, but if you're looking at the concentration of the hydroxide, we can also we call that the POH. So what's the power of the hydroxide, right? Acids and bases kind of go together. These are always going to be opposite of each other. So if you know the concentration of hydroxide, you can find the pH by taking the minus log of that concentration. So if you know the concentration, the molarity of the hydronium, take the minus log of that to figure out the pH. If you know the pH, put that as the exponent to 1 times 10 to that exponent to that negative exponent to get the concentration. Okay. Now we saw that the for water you have H2O, right? Dissociates into OH, so that the concentration of hydrogen and the concentration of the hydroxide have to, when you multiply them together, have to equal 1 times 10 to the negative 14th, right? So if you take 1 times 10 to the kW, that's the kW, remember that, 1 times 10 to the negative 14th, you divide that by the concentration of the hydroxide, or the hydronium, that'll give you the concentration of the hydroxide, and vice versa. Okay, so you can follow these arrows just like the map we've been using. Okay, if you have the concentration of hydroxide, you can get the POH by taking the minus log. So it's the same thing of that concentration. You get the POH. You take the P, if you know the POH, you can get the OH concentration by putting that to the exponent of the negative. So this box, very useful. And you've probably done this before, but the pH and the POH always have to add up to 14. Right, so if you know the pH, what plus that number plus what equals 14. So it's just 14 minus the pH, 14 minus the POH. Very useful box that I like to use. So here we have calculate the pH and the OH minus of 5 times 10 to the negative third. So this is the concentration. Right, this is the concentration of the, because it's an acid. If it gives the concentration of the base, then it would be the POH. Okay, so this would be, look at the pH of that. So the pH is equal to, come back over here, is equal to the 1 times 10 to the minus, or no, we know the concentration. We want to know the pH, so we want to take the minus log of this. So minus log of this concentration, 5 times 10 to the negative third. Okay, so we take our trusty calculator, 5 exponent 3 negative log of that, and make that negative. So the pH would be 2.3. Okay, see that? 2.3. Okay, notice this has one significant digit, so we'd go to the 10th place. pH would be 2.3. Alrighty. It says what's the OH minus concentration, right? So we know the concentration of the hydroxide is 5 times 10 to the, so 1 times 10 to the negative 14th is equal to 5 times 10 to the negative third times the concentration of the OH minus, right? So if we divide both sides by 5 times 10 to the negative third, cancels that. Concentration of the OH minus would be 1 exponent 1 exponent negative 14 divided by 5 exponent 3 negative equals. That equals, you can see it there, 2 times 10 to the, I don't know what that is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 12 molar OH minus, right? So that's an example of a strong acid problem. Sign one out of the book so you can practice. But here's the box one more time, just in case you didn't get it. Put some problems on strong acids. Let me know if you have any questions. Hopefully these are helpful. Having a lot of fun making these, actually. I'll do a weak acid example. I'll go over how to calculate the weak acid. It's much more difficult next.